Hello everyone, welcome to this NPTEL course on Advanced Prestress Concrete Design. We are going to start this module 6, which is for design of bond and anchorage zones. This will be divided into two parts. The first part, we are going to look at pre-tension members. In pre-tension members, how the transfer of prestress happens and what kind of transverse tensile stresses develop and how do we design for that. So, the expected learning outcomes, the student after going through the video should be able to understand the basic mechanism of pre-stressing transfer in the pre-tension concrete. They will be able to understand the stress distributions at the anchorage zones and will be able to gain knowledge on designing the reinforcement for anchorage zones in a pre-tension member. These are the three main learning outcomes from this part of the video. Okay, you all know that in pre-tension system, the pre-stressing steel is tensioned before the concrete is poured, right. First, the pre-stressing strand or cable is stretched and the concrete is poured. Then after setting the concrete, the pre-stressing strand will be cut. Only when you cut the strand, actually the transfer of prestress actually happens, right. So, this is how it is. The prestressing force is transferred to the concrete by means of bonding. So, you can see here bond stresses, they will develop at the interface of the prestressing strand and the concrete, and the stress will be transferred to the concrete, and it takes some distance before the prestressing steel develops its effective prestress. Okay. Now, there are two things when we talk about transfer of prestress in a pre-tension element. One is how much distance it takes to develop that effective prestress that we give it, right. And then the second one is at ultimate, for example, this is at ultimate, right. So, this is your effective stress. At ultimate, it is going to develop this maximum strength. So, for the ultimate condition, the stress should increase from effective prestress to whatever that failure condition that you are assuming. So, this is an incremental stress that develop. This is an incremental stress that develop at ultimate. Now, why is it important to understand this is, first is it takes some distance which is called transfer length to develop the pre-stressing, effective pre-stressing stress. Then due to the virtue of your external loads, it is stretched to much higher stress at ultimate condition. So, you have to have, when we say development length, we include both the transfer length and the bond length, which is we call that as LB, and transmission length or transfer length we call that as LT. So, that means my total development length to reach that ultimate stress requirement at ultimate, we need to have both LT and LB has to be added up to get development length. So, it has two components, one is the transfer length to transfer the effective prestress, and LB is the bond length that is required to develop that additional stress. Please note that typically we stress, right, initial prestress we put it as 0.75 times FPK, right, that is your jacking stress, that is quite high. And now, due to external loads, now this stress will further increase. Okay. So, due to losses, first it will become FPE, then FPE will become some stress FPS. This is due to external loads, right. So, this is effective prestress. After jacking, you will have some losses also that we need to account for it, and then due to external loads, it is going to develop into the higher strength that you are going to use it. Now, how does this bond helps in achieving that effective stress and the development length? The bonding happens through three main things. One is an adhesion that is basically bond between the steel surface and the cement paste. And then the next is the friction. The bond is also developed due to the roughness of the surface of the steel bars such as ribs. In case of pre-stressing strand, usually we use a 7-wire strand. So, there is always going to be the gaps between them. So, the concrete can go inside that and it develops a friction. So, it is a 7-wire. In a 7-wire strand, you know that around the central core wire, remaining other 6 wires are braided. So, there is a lot of gaps in which that concrete can fill in, and then it can create a lot of friction. Now, the next one is the shearing resistance. This is actually happening because of the dilatancy or the volume change that actually increases the mechanical interlocking between the pre-stressing steel and the concrete. So, these are the 3 main components through which the bond is developed. Now, let us look at again transfer zone, and transfer zone, as we have discussed, this is the zone or the length required from the free end for the pre-stressing strand to develop its effective pre-stress. So, the pre-stressing strand develops the effective pre-stressing source at a distance from the end of the member. This region is called as transfer zone. So, as soon as you cut the strand, right, the tendency of the pre-stressing strand is to actually go inside the concrete up to a certain distance. That is what we call that is a shrink of tendon, and then the bond is eventually developed. So, in the transfer zone, the tendons slip and they sink into the concrete after cutting. Actually, now we talked about the 3 sources of bond. When that happens, the adhesion is destroyed and the bond actually comes only from friction and shearing resistance that we talked about in the previous slide. Now, after the transfer zone, we call this as an intermediate zone. Now, here the bond stress is mainly resisted by adhesion and friction, and because in this zone there is no dilatancy, so the shear resistance is not much. The pre-stressing force is fully achieved in the concrete. So, whatever that pre-stress that you want to put, average pre-stress is happening only from the end of the transfer zone, okay, or at the beginning of the intermediate zone, right. Now, let us look at what is Hoyer effect. Hoyer, you know that he made a lot of contributions in the early developments of pre-stressing system, especially for pre-tensioning system, and we know that when you stretch the cable, the diameter of the cable. So, this basically is your diameter of the cable, original diameter of the cable, okay, diameter of the cable, that reduces to certain diameter ds. Let us say it reduces, d becomes ds while during the process of stretching, because when you stretch the wire, the diameter of the wire will or the strand will get reduced after stretching, right. So, there is a reduction in diameter because of the Poisson's effect. We know what is the Poisson's effect, okay. Though you are applying tension in the longitudinal direction, so there is going to be shortening of the diameter that is happening. After cutting the strand, as we have discussed previously, the pre-stressing steel sinks inside the concrete up to a certain distance, and in the end region, so what happens is, because the stress is not there, the strand regains its original diameter due to less stress. That means the diameter, the original diameter d, it tries to regain. After stretching, it becomes ds, then again it is can go back to the original diameter d at the free end, or I should say at the edge region. The diameter at the intermediate zone still will remain small, whatever that you have stretched it, ds, right. So, because of this change in diameter or from higher diameter to lower diameter, it creates this kind of a wedge, okay, creates this kind of a wedge action. So, which eventually helps in putting the inclined compressive stress to the concrete, that what you see here, okay. So, this is how the pre-stress is actually developed in the concrete in a pre-tension system. Okay. Now, let us see what is the transmission length. The length required for pre-tension member for fully transferring the effective pre-stressing force to concrete through bond is called as transmission length. Now, you can clearly see from here, after the strand is stretched, it requires some distance to achieve this effective pre-stress FPE. So, this distance that is required to reach that effective pre-stress is called as transmission length. Now, what are the factors that are going to influence the transmission length? The diameter of the wire or the strand. If you have a smaller diameter, for the same force, I can use smaller diameter of the strand. That means my surface area is going to increase. If I put more number of strands for the same force, the surface area is going to increase. So, it is, if smaller the diameter, smaller will be the transmission length. And then the surface characteristics of the strand. Now, the strand can have different surface characteristics. People during manufacturing process, they create purposefully some indentation or some small holes or some patterns on the strand. If it is able to have larger surface irregularity, or I should say surface unevenness, then it will be able to develop that effective pre-stress in a shorter length. Okay. So, the surface characteristics of the strand also matters. If it is a very smooth plain strand, it will take longer distance for reaching that effective pre-stress. Now, in addition to that, again the coefficient of friction between the steel and concrete also plays a role. Higher the coefficient of friction, higher will be the friction generated, bond generated through friction. So, it will require less transmission length. Then also the elastic properties of the steel and concrete. And we know that concrete, higher the grade of concrete, higher will be your bond strength. Again, that also helps in reducing your transmission length. Now, higher he proposed some equation to calculate the transmission length by considering this wedge action and the Poisson's effect of the pre-stressing steel. Now, you can see here LT is given by some equation which is phi divided by 2 into nu into 1 plus Poisson's ratio nu c, okay, and alpha e is nothing but your modular ratio, that is the ratio between the elastic modulus of steel to concrete, and it is also a function of your initial pre-stressing FPI and also the difference between the initial pre-stressing and the effective pre-stressing. So, all these important parameters are put into this equation using elastic stress analysis. Hoyer derived this equation and it was also validated through some experimental testing. So, this helps in estimating this transfer length. So, it is function of the elastic modulus of the materials, Poisson's ratio of concrete and friction coefficient that is developed between the steel and concrete, and more importantly the diameter, right. Okay. So, what we can see, as we have said, because of this wedge action, we say that the inclined compressive stresses are going to develop, but while in the process of developing this inclined compressive stresses in the radial direction, I also develop transverse tension that I need to be careful about. Okay. So, you have transverse compression that is happening. In addition to that, you also develop transverse tension that is going to develop. Now, you can see here that as per IS 1343, if the strength of the concrete at transfer is not less than 35 megapascal and if the tendon is released gradually, right, that means the strength should be at least 35 megapascal while you do the release of pre-stress or while you transfer the pre-stress or while you cut the strand in pre-tension system, and you need to cut also in a proper pattern. You cannot abruptly in a fast manner, you cannot typically people use a torch to cut the pre-stressing. If you do with very high heat and then if you do it very quickly, then you may develop some higher transverse tension, which is not good. So, we need to also do it in a very sequential, in an orderly fashion, the cutting of the strand. For plain and indented wire, the transfer length is given as 100 times the diameter of the wire. For crimped wire, it is given as 65 times the diameter of the wire. For strands, it is given as 30 times the diameter of the wire. This is the transmission length, or you say transfer length. Okay. Now, that previous equation had lot of parameters that again was further simplified by Krishnamurthy and Marshall way back in 1960s, and they proposed a very simplified expression only as a function of your concrete strength. So, FCU is a cube compressive strength at transfer, and beta is a constant that depends upon the wire or a strand. So, people have tested different diameters, wires, strands, right, and different range of diameters, and also twisted wires, and they come up with this beta coefficient, you can see, right. So, depending upon what type of diameter and what type of pre-stressing steel that I am using, I can select the beta and I can plug into this simple empirical equation to find out what is the transfer length or transmission length. Both are same. Now, let us talk about in the transmission length how the bond stresses are changing. So, we have studied what is transmission length. Now, within the transmission length, how the bond stresses are developing. And we know that at this location, at the free end, you're going to have 0 bond stress, because we said initially that pre-stressing steel will shrink or sunk into the concrete little bit for a little distance. And also in the transmission length, the strand experiences a local gradient as well as a strain gradient, and the strain gradient can cause slip in the particular portion, right. So, because again, how does the strain gradient comes, how does the load gradient comes? Again, depending upon your external loads, you are going to have variations in your bending moment and shear force and so on. Now, why the bond stresses are decreasing in the transfer region? In the inner region, as we have explained previously, the strand is not able to regain its original diameter, right. Only in the close to the end region, edge region, you have less stress requirements. So, the strand is able to regain to its original diameter, but however, as you go inside, the strand will not be able to regain its original diameter. So, the wedge action will get diminished. So, that diminishes the contact area and thus reduces the friction between the concrete and strand. So, that is the reason you develop a very high bond stress and then you kind of go like this. But what we do is we take an average bond stress in our calculation. So, there is a lot of local variations that are happening, but we say in the transmission range we deal in terms of average bond stress. Okay. Let us say the area of this actual variation is equal to a rectangular area like this. Okay. So, if this area and this area is kept same, then we can say this is the way that you calculate your average bond stress. Okay. Now, in addition to the transmission length, that is what we call that as a transfer bond, you also develop, because of the load effects, a flexural bond. Now, what is flexural bond? For plane sections to remain plane, the strain in the embedding reinforcing bar is assumed to be same as that of the surrounding concrete. This is a fundamental assumption that we make for Euler-Bernoulli's bending theory, right. So, to achieve the strain, linear strain condition, we need to make sure that the bond force is developed on the interface between the concrete and steel, so that the slip is not occurring at the interface, right. So, this is a simply supported beam with a 2-point load, you can see. If I take a small region between the, let us say, the support A and this is B, close to the support A, two sections, section A and section B, and then I look at what is the internal forces that are there. You know that here for this particular beam, you know that the bending moment is like this, right. So, at these two locations, you know this is M1 and this is M2. So, you see that the bending moment is increasing, right. So, this is moment at the left side and the right side, and there is going to be an increment in your moment, m1 increases to m2. So, that is what it is written as m plus dm. Now, to resist this moment m, I need to develop forces in the concrete. Concrete will give me compression force, steel will give me tension force. That is your internal forces to resist this bending moment, right. So, the C into the lever arm has to resist this bending moment, that what I am going to have on this section. Similarly, if you look at it on the right side, now that moment has increased from m to m plus dm, similarly the compression force has to increase C plus dc and tension force has to increase to T plus dt. Now, see that shear force in this region A and B is always constant for this particular loading configuration. So, that is why the shear on the left side and right side is same, but only the directions will be different. Now, to satisfy this, if I just take the free body diagram of the reinforcing steel or a pre-stressing steel and I look at it, on the left side I am going to have tension force T, and this right side the tension has to increase to T plus dt to resist this increased bending moment, right. Now, how do we develop this dt? So, to satisfy this horizontal force equilibrium, now I need to develop these bond stresses on the interface. Okay. So, these stresses are called flexural bond stresses, which develop at the interface of the steel to cater to the increase in the bending moment that further requires that tension in the rebar or pre-stressing steel to reach a higher value. So, this is the AB portion. Similarly, when you look at it, so you have to look at this is a all the stresses develop on the perimeter of the pre-stressing steel, right, or a rebar. So, if you look at this CD portion, again you can see here, because at the location C the bending moment is 0. So, your bond stress will be 0 and then it will increase to higher value of D. So, here it is 0 force, here it is some tension force T. So, you can see in the CD portion, this is the way that you develop your bond because of the increase in your bending moment. Okay, there are two things. One is a bond required to develop that force, which is called as for transfer length. The second one is because of the load effects, the increase in bending moment, again you need to develop some additional bond stresses, which are called flexural bond stresses. Now, again we have discussed what are the sources of bond strength. There is going to be a weak chemical adhesion that will basically like a gum like property that will form during the hydration process. Again, mechanical friction between pre-stressing steel and I should say pre-stress, right, and concrete, and slip induced interlocking of natural roughness of the strand or tendon with the concrete, and indented strands. Again, indentation means there is some patterns that will be created on the surface purposefully to increase the bond. So, that provides bond force via patterns on the strand that develops a good bond with the surrounding concrete. Sometimes what happens, we also put some end anchorages, hooks, and providing tie arch action even for a broken bond beam. So, this is in pre-stressing steel we cannot do that. Maybe in post tension system with anchorages it kind of helps, but in a pre-tension system we cannot have this end anchorages. Maybe what we can do is we can put some lot of local confining steel to create this. Okay. So, this is the thing. Now, what is the force in the steel? For example, this is what we talked about. Even though bond is not there, still through tied arch action I can develop or resist the applied load. Okay. So, this was said, provided at this location my steel is anchored really well. Okay. If it is not going to slip at the edge, then still I will be able to develop this tied arch mechanism for transferring the forces, right. So, that is also possible. Now, let us look at what is the actual distribution of flexural bond stresses. Okay. Again, we are taking a simply supported beam subjected to 2 point loads in the middle, and this is your bending moment diagram, you know that. And if you look at it, though I have bending moment is varying, and even in the middle region you have a constant bending moment. But what you will see here is the cracks are not happening everywhere. The cracks are happening only in a certain, wherever there is a weak link, the crack will form initially, and then the crack will progressively move towards the supports with increase in the loading. But not the entire, though this region is subjected to same bending moment, not all the locations are cracked, the cracks are happening only at some discrete locations. So, only at the cracked location, if I take a section, the steel will have very high stress. But in between the crack, when you look at it, okay, for example, if you look at this region, okay, so there is no crack, right. So, that means at that section when I take it, concrete can still offer me tensile strength, right. So, that is what we are saying here. The stress in the steel, wherever crack is forming, it is going to increase and decrease and decrease and increase like this, right. So, you are going to have this kind of a stress variation that is happening, right. Wherever I am going to have a crack like this, at this location the stress is going to be high. But between the cracks, now concrete is also helping me in tension strength. So, I am going to have less stress in the steel. So, that is this location. This location, if you see, there is no crack. For example, here there is no crack. So, that is the reason my stress in the steel has slightly come down, again it is picking up. Now, again you can see here tensile stress in the concrete also will be like at cracked location there is no concrete. So, the stress, these are all the locations of your cracks, there is no, just exactly in between the crack you get maximum stress, tensile strength of the concrete. So, from this we can see that the flexural bond stress will be in and out. So, you can also explain this from a free body diagram. So, you can see here that the flexural stresses will change directions wherever the concrete is contributing like this. Okay. Of course, at the crack location there is no contact. So, there is no bond, it is only the steel that is taking all the tension. But in between them at the interface, because concrete is connected with the steel, so it is helped me in achieving that increase in tension in the steel by the virtue of bond, right. So, the concrete again is said fails to resist tensile stresses only when there is an actual crack located. So, the steel T is maximum and T max will be M by JD. Now, between the cracks the concrete does moderate resist tension introduced by bond. Now, this bond stress is proportional to the rate of change of bar force, that means it is proportional to the bending moment that it is seeing. It is highest where the slope of the steel force curve is greatest. So, that means, so the steel force is this, wherever the slope is high, that is a location that I am going to have high bond stress. Okay. So, there is going to be a very high local bond stress that are going to be developed at the crack locations, but we do not explicitly look at it. What we really do here is we take the average again bond stress, even in the in and out bond stress we take the average bond stress for calculations. So, again there are two things, one is the bond stress that are developed because of the to transfer the pre-stress in case of a pre-tension system. In addition to that, if there is an increase in bending moment, then the pre-stressing steel tension also should increase. At that time you develop flexural bond stress. Okay, so this is again we say this is for an uncracked section. Let us see how to find the expression for this flexural bond stress. I take and let us say that the loads are very less and then the section is not cracked, okay, and this is a pre-stressing beam with a cable profile and it is subjected to some load like this. Let us take a section between x and y, and again bending moment is mx at the left side, and then at the right side I have bending moment is my. Let us say that the shear is constant for this particular loading configuration, and pre-stressing cable is at a distance of y from the CG of the cross section. If I take the free body diagram of the steel, pre-stressing steel, I take a very small elemental length, let us say between x and y. On the left side I am going to have tension force Fx, on the right side I am going to have pre-stressing force or tension force, which is Fy. Now, the difference between the bending moment should be equal. If I take the moment about this point, you see that My minus Mx, they are acting in the opposite direction, should be equal to V into this is the distance dx to satisfy moment equilibrium, right. Now, what is My? We know that we are looking at the stress, let us say at the location, because the system is now uncracked, please note that. So, if I can find out the stress, how do we find out the stress? Let us say I assume some stress, which is let us say Fy on the right side. So, if I know the stress multiplied by I by y will give me the moment that it is causing that stress Fy. Similarly, at x it will be Fx into I by y. So, we do some simple simplifications to get what is the expression for your flexural bond stress. That is what we are interested in. Now, if you go back V dx again, if you can take for example, you see here, now what is if I multiply both sides by alpha e into as on both denominator and numerator, and you will find that if I can take I out, right. So, I and y if I take it out, then you will find that alpha e into as into Fy minus alpha e into as into Fx. All I am doing is both sides I am multiplying by this, right. It is consistent. So, then only I can develop a simplified expressions in terms of parameters that I have it in my hand, right. So, we know from our working stress method, we use this when the system is uncracked, everything is elastic. So, the stress of different materials can be calculated using modular ratio concept, where alpha E is the modular ratio between ES and EC, and ES is the shear reinforcement that we have. Sorry, I think so. This should be steel. I think just say it put steel. Okay. And in this formula, now if you look at it, now if I take this V into dx, we can write that as I by y. Everything is same. So, we can in a way we can write this as the stress or the force at the location Fy minus the force in the location section x. Okay. So, that is V into dx. Now, what is the difference between Fy and Fx? That is what we are trying to calculate, which is nothing but this difference in the force. If I take the free body diagram of the pre-stressing steel, now you find that this is nothing but your tau b into the perimeter into dx. So, the difference force basically is tau b into sigma o is the force. Now, if this element length is dx, okay, sigma o is basically the perimeter multiplied by length will give me the surface area. Surface area into the bond stress will give me the force that is acting, interfacial force, bond force that is acting at the steel, right. So, in this way I can calculate this. So, you can otherwise we can say the average bond stress can be expressed as alpha E into As into y into V divided by IO. Now, dx will get cancelled in both sides. So, we can write the flexural bond stress as a function of shear that is acting in that particular cross section, and flexural moment of inertia is known. If I know the details of the pre-stressing steel, I can calculate the perimeter of all the pre-stressing steel, and As or AP is the pre-stressing steel area that you have, and y is the distance of the steel, okay, flexural steel. I should say this is a flexural steel reinforcement, right, not shear. So, in this way flexural bond stress can be calculated as a function of shear that is in the cross section and the sectional detail that I have in terms of your flexural steel and the distance of the flexural steel, and the diameter characteristics will help me to calculate my perimeter. Okay. So, this is what that is for an uncracked section. Now, how do we do that for a cracked section? So, these are the two conditions. So, one is for flexural bond stress using uncracked condition, the next one is for the cracked condition. Now, again the same thing we look at this. Now, only thing is the section is cracked, the stress ranges have become non-linear. So, that is the reason you see here concrete, I get this kind of a parabolic stress distribution, and let us say that it is getting close to that of ultimate, right. So, again for the same 4-point loading configurations, you will find that the shear on the left side and right side is constant because there is no load, right. So, there is no change in the load, right, and then the tension left side I have tension force T and the right side I have T plus dt, and if you take the free body diagram like we have discussed, this is going to be T and this is going to be T plus dt. Now, as we have explained previously, the change in the tension force dt can be converted as change in your bending moment divided by the lever arm, which we talk in terms of JD. So, for the local equilibrium, we know that the change in bar force is equal to bar force at the contact surface, right. So, this is the free body diagram of the rebar. The same stresses will act on the concrete surface as well to maintain equilibrium. So, now what is that it is causing this dt, T and T will get cancelled, dt will be equal to tau b into the perimeter times the distance will give me the surface area. So, shear stress multiplied by surface area is that force that it is developed, the bond force that is developed on the bar, that is what it is creating, that increase in tension dt, right. So, we have seen that. Now, what is tau b? dt divided by summation of perimeter multiplied by dx, or in other words we can write dt as dm by jd, right. So, this is the dd, or in other words dm by dx is what, which is your change in shear, which is dV. So, we can write dV by jd into perimeter area. So, this is the expression for your flexural bond stress. Again, first case we did for a uncracked section, this is for a cracked section. Again, it is function of your shear that is acting in the cross section times here the lever arm also comes, JD that comes, and then the perimeter that what it is acting. Okay. This is for one particular cross section, only perimeter that it is coming, right. So, per unit length you can see.